25 ohm rule for electrode-to-earth connection was developed based on extensive research and analysis of electrostatic discharge, also known as ESD phenomena. The rule aims to provide a safe and effective means of dissipating static charges from metallic objects to the earth, preventing the accumulation of dangerous charges that could lead to electrical accidents. The mathematical principles behind the 25 ohm rule involve concepts from electrostatics, including Coulomb's law and Gauss's theorem. Coulomb's law describes the electrostatic force between two charged particles, while Gauss's theorem relates the electric field around a charge to the charge itself. The 25 ohm rule is based on the time-domain analysis of ESD events. When a high voltage surge strikes a metallic object, it creates an electrostatic charge. This charge will dissipate over time as it interacts with the Earth's potential. The rate of dissipation is directly related to the resistance between the object and the Earth. Through extensive experimentation and analysis, it was determined that a resistance of 25 ohms or less provides the optimal balance between safety and effectiveness. With a resistance below 25 ohms, the electrostatic charge will dissipate quickly enough to prevent the accumulation of dangerous levels of charge. The 25 ohm rule is a crucial safety measure in various industries and applications where ESD can pose a significant threat. It is commonly applied in the grounding of electronic equipment, lightning protection systems, and high-voltage installations. By adhering to the 25 ohm rule, engineers can ensure that static charges are safely and efficiently dissipated to the Earth, minimizing the risk of electrical accidents and damage. Static electricity, the buildup of electrical charges on a surface, is a common phenomenon that can occur when two materials are brought into contact and then separated. This contact and separation can cause electrons to transfer from one material to the other, creating an imbalance of charge. One material becomes positively charged, having lost electrons, while the other becomes negatively charged, having gained electrons. The amount of charge transfer depends on several factors, including the materials involved, the surface area in contact, and the speed of separation. When a charged object comes into proximity with another object that has a different electrical potential, a sudden flow of electricity, known as electrostatic discharge or ESD, can occur. This discharge is an attempt to neutralize the charge imbalance. ESD events can range from a harmless spark to a destructive surge of energy depending on the amount of charge accumulated and the resistance of the path through which the discharge occurs. In many industrial settings, ESD poses a significant risk to sensitive electronic equipment and components. The rapid discharge of static electricity can generate high voltages and currents that can damage or destroy electronic circuits. This can lead to equipment malfunctions, data loss, and costly repairs or replacements. To mitigate the risks associated with ESD, various protective measures are implemented, including grounding, shielding, and the use of static dissipative materials. Grounding provides a low-resistance path for static charges to flow safely to the Earth, preventing the buildup of dangerous voltages. Shielding involves enclosing sensitive equipment or areas with conductive materials that block electromagnetic fields and prevent ESD events from reaching the protected area. Static dissipative materials are designed to slowly dissipate static charges, reducing the risk of sudden and damaging discharges. The 25 ohm rule is a specific guideline used in grounding systems to ensure effective dissipation of static charges. It states that the resistance between a grounded object and the Earth should not exceed 25 ohms. This low resistance allows static charges to flow quickly and safely to the Earth, minimizing the buildup of voltage and reducing the risk of ESD events. The rule is based on the principle that a lower resistance path provides a more effective means of dissipating static charges. The mathematical basis for the 25 ohm rule can be understood through the application of Ohm's law, which states that the voltage across a resistor is equal to the current flowing through it multiplied by the resistance. In the context of ESD, the voltage is the electrostatic potential of the charged object, the current is the flow of charge during the discharge, and the resistance is the resistance of the grounding path. By limiting the resistance to 25 ohms or less, the voltage buildup on the charged object is minimized, reducing the potential for damaging ESD events. The 25 ohm rule is not a universally applicable standard and may not be appropriate for all situations. The specific grounding requirements for a particular application depend on various factors, including the sensitivity of the equipment being protected, the environment in which it is used, and the applicable regulatory standards. In some cases, more stringent grounding requirements may be necessary to provide adequate protection against ESD. For example, in highly sensitive electronic manufacturing environments, the resistance to ground may need to be significantly lower than 25 ohms. Conversely, in less sensitive applications, a higher resistance to ground may be acceptable. The 25 ohm rule serves as a general guideline and a starting point for designing grounding systems. It is important to consult with qualified engineers and safety professionals to determine the appropriate grounding requirements for a specific application. The effectiveness of a grounding system also depends on the quality of the grounding connections and the overall design of the grounding network. Grounding connections should be clean, tight, and corrosion resistant to ensure a low resistance path for static charges to flow to the earth. The grounding network should be designed to minimize ground loops and other potential sources of noise and interference. Regular inspection and maintenance of grounding systems are essential to ensure their continued effectiveness. Grounding connections should be checked periodically for corrosion, looseness, and other signs of degradation. Grounding conductors should be inspected for damage and replaced as needed. Ground resistance measurements should be taken regularly to verify that the grounding system is still meeting the required resistance levels. In addition to grounding, other ESD control measures may be necessary to provide adequate protection for sensitive electronic equipment. These measures include the use of static dissipative workstations, wrist straps, and clothing. Static dissipative workstations provide a controlled environment where static charges can be safely dissipated. Wrist straps provide a direct connection between the operator and ground, preventing the buildup of static charges on the operator's body. Static dissipative clothing helps to minimize the generation of static charges due to friction between clothing and other materials. A comprehensive ESD control program should include training for employees in the proper handling of static-sensitive devices and the use of ESD control measures. Employees should be trained to recognize the risks associated with ESD and to take appropriate precautions to prevent ESD events. The training should cover topics such as grounding, shielding, static dissipative materials, and proper handling techniques. The 25 ohm rule is a valuable guideline for ensuring the effective dissipation of static charges in grounding systems. However, it is important to remember that it is just one component of a comprehensive ESD control program. A combination of grounding, shielding, static dissipative materials, and employee training is necessary to provide adequate protection for sensitive electronic equipment. Furthermore, understanding Coulomb's law provides a foundational understanding of the forces at play. Coulomb's law, a fundamental principle in electrostatics, quantifies the electrostatic force between two charged particles. This law, formulated by Charles Augustin de Coulomb in the late 18th century, states that the force between two-point charges is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. Mathematically, Coulomb's law can be expressed as follows: force equals K times Coulomb times Q2 divided by R squared. Where force is the electrostatic force between the charges, K is Coulomb's constant, a proportionality factor that depends on the units used. Coulomb and Q2 are the magnitudes of the two charges, and R is the distance between the charges. The force described by Coulomb's law is a vector quantity, meaning it has both magnitude and direction. The direction of the force is along the line joining the two charges. If the charges have the same sign, meaning both are positive or both are negative, the force is repulsive, pushing the charges away from each other. If the charges have opposite signs, one positive and one negative, the force is attractive, pulling the charges towards each other. Coulomb's law is a cornerstone of electrostatics, providing a quantitative description of the electrostatic force that governs the interactions between charged particles. It is essential for understanding a wide range of phenomena, from the behavior of atoms and molecules to the operation of electronic devices. Gauss's law also plays a vital role. Gauss's law, another fundamental principle in electrostatics, provides a relationship between the electric field and the distribution of electric charges. This law, formulated by Carl Friedrich Gauss in the 19th century, states that the total electric flux through any closed surface is proportional to the enclosed electric charge. Mathematically, Gauss's law can be expressed as follows. The closed integral of E dot d equals Q enclosed divided by epsilon naught, where the closed integral of E dot d represents the electric flux through the closed surface. E is the electric field vector, d is the differential area vector of the surface, Q enclosed is the total electric charge enclosed within the surface, and epsilon naught is the permittivity of free space, a constant that relates the electric field to the charge density. Gauss's law is a powerful tool for calculating electric fields, especially in situations where the charge distribution has a high degree of symmetry. By carefully choosing the closed surface, known as a Gaussian surface, it is possible to simplify the calculation of the electric flux and determine the electric field. For example, consider a uniformly charged sphere. By choosing a spherical Gaussian surface concentric with the charged sphere, the electric field will be radial and have the same magnitude at all points on the Gaussian surface. This simplifies the calculation of the electric flux, allowing the electric field to be easily determined using Gauss's law. Gauss's law is also useful for understanding the concept of electric shielding. A conductor in electrostatic equilibrium has no electric field inside it. This is because any electric field inside the conductor would cause charges to move, violating the assumption of electrostatic equilibrium. As a result, a hollow conductor can be used to shield its interior from external electric fields. This principle is used in many applications, such as shielding electronic equipment from electromagnetic interference. In summary, Coulomb's law and Gauss's law are fundamental principles in electrostatics that provide a quantitative description of the electrostatic force and the relationship between the electric field and the distribution of electric charges. These laws are essential for understanding a wide range of phenomena, from the behavior of atoms and molecules to the operation of electronic devices. Furthermore, to elaborate on high-voltage surges, a high-voltage surge is a transient electrical event characterized by a sudden and significant increase in voltage within an electrical system. These surges can be caused by a variety of factors, including lightning strikes, switching operations, and equipment failures. High-voltage surges can have devastating effects on electrical equipment and systems, causing damage, malfunction, and even complete failure. Understanding the causes and effects of high-voltage surges is crucial for implementing effective protection measures. Lightning strikes are a major source of high-voltage surges. When lightning strikes a power line or nearby structure, it can inject a large amount of energy into the electrical system, causing a sudden and dramatic increase in voltage. These surges can travel long distances through the electrical grid, affecting equipment far from the point of impact. Switching operations, such as turning on or off large electrical loads, can also generate high-voltage surges. These surges are caused by the sudden changes in current flow that occur during switching operations. The magnitude of the surge depends on the size of the load being switched and the characteristics of the electrical system. Equipment failures, such as short circuits or insulation breakdown, can also lead to high-voltage surges. These surges are caused by the sudden release of energy that occurs during the failure. The magnitude of the surge depends on the amount of energy stored in the system and the characteristics of the failure. High-voltage surges can have a variety of damaging effects on electrical equipment and systems. These effects include insulation breakdown, component failure, and data loss. Insulation breakdown occurs when the voltage surge exceeds the dielectric strength of the insulation material, causing it to fail and create a short circuit. Component failure can occur when the voltage surge exceeds the voltage rating of electronic components, causing them to overheat and fail. Data loss can occur when the voltage surge disrupts the operation of electronic devices, causing them to lose or corrupt data. To protect electrical equipment and systems from high voltage surges, various surge protection devices, also known as SPD, are used. SPD are designed to divert the surge current away from sensitive equipment and safely to ground. SPD are typically installed at the service entrance of a building and at the point of use for sensitive equipment. There are several different types of SPD available, each with its own characteristics and capabilities. Some common types of SPD include metal oxide varistors, also known as MOV, silicon avalanche diodes, and gas discharge tubes. MOV are the most common type of SPD. They are voltage-dependent resistors that have a high resistance at normal voltages but a low resistance at high voltages. When a voltage surge occurs, the MOV resistance drops, diverting the surge current to ground. Silicon avalanche diodes are another type of SPD. They are semiconductor devices that have a high resistance at normal voltages but a low resistance at high voltages. When a voltage surge occurs, the diode breaks down, diverting the surge current to ground. Gas discharge tubes are another type of SPD. They are gas-filled tubes that have a high resistance at normal voltages but a low resistance at high voltages. When a voltage surge occurs, the gas in the tube ionizes, creating a conductive path that diverts the surge current to ground. In addition to SPD, other measures can be taken to protect electrical equipment and systems from high voltage surges. These measures include proper grounding, shielding, and surge-resistant design. Proper grounding provides a low impedance path for surge currents to flow to ground, reducing the voltage buildup on equipment. Shielding involves enclosing sensitive equipment or areas with conductive materials that block electromagnetic fields and prevent surge currents from reaching the protected area. Surge-resistant design involves using components and materials that are less susceptible to damage from high-voltage surges. A comprehensive surge protection strategy should include a combination of SPD and other protection measures. The specific measures that are appropriate for a particular application depend on the sensitivity of the equipment being protected, the environment in which it is used, and the applicable regulatory standards. Regular inspection and maintenance of surge protection systems are essential to ensure their continued effectiveness. SPD should be checked periodically to verify that they are still functioning properly. Grounding connections should be inspected for corrosion, looseness, and other signs of degradation. Surge protection systems should be tested regularly to verify that they are providing adequate protection against high voltage surges. High voltage surges are a serious threat to electrical equipment and systems. By understanding the causes and effects of high voltage surges and implementing effective protection measures, it is possible to minimize the risk of damage, malfunction, and failure. In discussing the dissipation of static charges, the dissipation of static charges is the process of neutralizing an imbalance of electrical charge on an object or surface. Static charge buildup can occur due to various mechanisms such as friction, induction, or contact with a charged object. If left unchecked, static charges can lead to various problems, including electrostatic discharge, which can damage sensitive electronic components, ignite flammable materials, or cause uncomfortable shocks. Several methods are used to dissipate static charges, including grounding, ionization, and the use of antistatic materials. Grounding involves providing a conductive path for the static charges to flow to the earth, effectively neutralizing the charge imbalance. This is typically achieved by connecting the charged object to a grounding electrode, such as a metal rod driven into the ground. Grounding is an effective method for dissipating static charges from conductive objects, but it is not suitable for non-conductive materials. Ionization involves creating a cloud of ions, which are atoms or molecules that have gained or lost electrons, in the vicinity of the charged object. These ions can neutralize the static charges on the object by either donating or accepting electrons. Ionization is typically achieved using devices called ionizers, which generate ions using various methods, such as corona discharge or radioactive sources. Ionization is effective for dissipating static charges from both conductive and non-conductive materials, but it can be expensive and requires careful control to avoid generating harmful ozone. Antistatic materials are materials that are designed to resist the buildup of static charges. These materials typically have a slightly conductive surface that allows charges to dissipate gradually. Antistatic materials are used in a variety of applications, such as clothing, packaging, and flooring. Antistatic materials are effective for preventing the buildup of static charges, but they may not be able to dissipate existing static charges quickly. The choice of method for dissipating static charges depends on the specific application and the properties of the materials involved. For conductive objects, grounding is often the most effective and economical method. For non-conductive materials, ionization or the use of antistatic materials may be necessary. In some cases, a combination of methods may be used to achieve optimal static charge dissipation. In addition to these methods, several other factors can affect the dissipation of static charges. These factors include humidity, temperature, and the presence of contaminants. High humidity levels can increase the conductivity of the air, making it easier for static charges to dissipate. High temperatures can also increase the conductivity of materials, facilitating charge dissipation. Contaminants, such as dust and dirt, can interfere with charge dissipation by providing insulating layers that prevent charges from flowing freely. Therefore, it is important to maintain a clean and controlled environment to ensure effective static charge dissipation. Proper static charge dissipation is essential in many industries, including electronics manufacturing, healthcare, and aerospace. In these industries, static charges can damage sensitive equipment, cause product defects, and even create safety hazards. By implementing effective static charge dissipation methods, these risks can be minimized. In conclusion, the dissipation of static charges is a critical process for preventing various problems caused by static charge buildup. Several methods are used to dissipate static charges, including grounding, ionization, and the use of antistatic materials. The choice of method depends on the specific application and the properties of the materials involved. By implementing effective static charge dissipation methods and controlling environmental factors, it is possible to minimize the risks associated with static charges.